Okay, so good morning, everybody. Also, good morning to the students in Kazan. So I already wrote some comments here for today. So next week we will go to completely online mode. So no change for the students from Kazan, but the students in Germany, they should visit this link here to join our WebEx session. And I also wrote down some comments regarding the exam. So I spoke to Mike Wolf and we decided not to shift the exam for the students from Germany. So yeah, it's easier for you and you have some more time for preparation. So right now the exam is scheduled on March 7th. You'll find this information also in the open timetable system of the university. So we will have the exam as it is scheduled. And for the students in Kazan, I asked Dr. Korobkov to look for a good time slot for you, Kazan, so that we don't get interference with other exams and also not with our lecture, which we will have on Tuesday then. Okay, and this is the time where I thought it's feasible because I also need like 1 or 2 days to check the exams, but this way we will make sure that students from Kazan get their grades in time. So I'm still waiting for a response from my colleagues in Kazan when the actual date and time will be. But just take it right now as orientation. So this is our current plan to go for this days. Okay. Are there questions regarding the organizational stuff? So as soon as I get the concrete date and time, of course, I will let you. Okay, so let's go back to what we did last time for our short repetition. Last time, we started to talk about the block codes, starting with a famous class of single error correcting codes, the famous Hamming codes, discovered already in the 40s. And we also made up some theory about this, but it is straightforward. So of course, depending on how many check bits I invest, this will basically determine the number of errors that I can detect. So for example, if I have a code word of length n, then of course, all of these n bits could be wrong. So it would be n possibilities how single errors could occur in this code word, and we could have the no error case. So for a code word of length n, we can get n plus 1 patterns that we would have to distinguish with our bits. And from this, we could basically derive the number of information bits that we can transmit for a specific code word length. So for a code word length of 7, we need 3 check bits to identify single errors, which means 4 bits for information remain. So this is why we have a 4,7 Hamming code and not something like a 7,4 Hamming code and not a 6,4 Hamming. And the next one, which would be reasonable, would be the 15,11 Hamming code, where we use 4 parity bits, 4 check bits, to identify single errors in this code word of length 15. So we can have 15 single error cases and the no error case. So with 4 bits, we can distinguish this 16 patterns in this case. This means 11 bits remain to carry our information. So then we thought about Hamming's idea how to calculate this parity bits in a smart way, such that each single error will basically give us a unique pattern in this mismatch of parity bits. For example, if U0 is transmitted wrongly, we will see that this parity P2 will not match anymore. The sum over all these guys will not be 0, it will be 1. Also here the sum over the blue guys will be 1, and the sum over the orange guys will be 0, as we have no error there. So we know we have an error in the blue circle, in the green circle, and not in the orange circle, which means only U0 can be. So in any case, any bit that will be corrupted by error, we could identify it uniquely. We will see today actually how this decoding be done in practice. But just now from the idea, from the theory, it's obvious we can identify single errors if we do it this way. Then we got to know the matrix vector notation for this encoding procedure. So this means if we want to encode any information bits in this vector u here, we can get this by multiplying with a so-called generator matrix, which basically defines how this parity bits, how the check bits are calculated. So if we want to get a systematic code where we basically find our information bits like as a part of the code word, we see we can achieve this by introducing an identity matrix here in this generator matrix G. This basically just has the consequence that the bits here get mapped directly in the code word as we see it here. And here, these columns of this parity matrix, actually here's a mistake, let's correct this. It's the parity matrix and parity check matrix. So the columns of this parity matrix basically define how these parity bits get calculated. We have the 1, 1, 1, 0 here. This means we get first information bit plus the second information bit plus the third information bit and not the fourth one. So this is the modulo 2 sum here over our first 3 information bits and so on. Simply, we can derive this from our coding scheme. We will also solve a task related to this today, that you get a better feeling how to get this generator matrix for certain coding schemes. So and with this generator matrix, we can get all valid code words, so our set of code words gamma. And yes, we get this set of code words by just multiplying any information sequence here, any sequence u, with the generator matrix. Yes, but this is straightforward. So we can get the 0, 0, 0 here multiplied with the generator matrix will be the all 0 code word. Next, the 0, 0, 1 multiplied with the generator matrix, we get the next code word. So by multiplying all possible info sequences, we will get a set of code words. Yes, and we thought a little bit more about this generator matrix. So for example, if we information words here with just a single one, for example, here at the last position, this one we saw will basically just pick the last row of the generator matrix here. So this means all rows of the generator matrix will be valid code words. So we already know 4 valid code words from our set of code words, actually the rows of G. And even one more, we also know the all 0 code word is a valid code. Just from looking at the generator matrix, I can already tell you 5 of the code words. Okay, so far about the generator matrix. And then we got to know the orthogonal complement of the generator matrix, the so-called parity check matrix H. So we could also define our set of code words in a different way. We could say the code words are all code words that are orthogonal to this matrix H or H transpose. Ways to define our code words: one way, multiplication with the generator matrix; the other way by saying all code words that are orthogonal actually to the rows of H or the columns of H transpose. And as this H matrix is a bit difficult to understand, I came up with this explanation here, actually by coming up with a useless example. So of course this generator matrix would not make sense. If you look at this, we would have two information bits that get mapped in the code word, and the parity bit will be 0 times the first bit plus 0 times the second bit. So this is a completely useless generator matrix, but it's small enough such that we can draw. So, and what we illustrate here is basically, again, that the rows of this generator matrix span the space of the code words. So here the yellow and the green one, draw them in this plane. They span the space where we find all valid code words. So all linear combinations of these rows of G are our valid code words. In our case, it's very simple. We have the most easy linear combination, 0 times the yellow one plus 0 times the green one, it's this one. And we have one more possible linear combination, the green one plus the yellow one, it will be this one here. So we get 4 possible code words as the linear combinations from our rows of G. So of course, if we have a larger matrix G, it's possible to draw. But here, for understanding, this is good. Keep in mind, rows of G span the space of code words. We find all valid code words by all linear combinations of the rows of G. Then the one which was more difficult to understand was this parity check matrix H. It is basically the matrix where the rows of the matrix are orthogonal to the rows of the matrix G. As our example is small enough, we can also draw this one. So the matrix H would go up now here, and you see all rows of G, yellow one and the green one, are orthogonal of H. Build the scalar product 1, 0, 0 times 0, 0, 1, it will be 0. And if you build the scalar product of the green one with the red one, it will be also 0. So any valid code word, also here this one, 1, 1, 0, that I multiply with the rows of H, the result will be 0. All valid code words are orthogonal rows of H. So we will use this matrix H later on to check if any received sequence is a valid code word or not. The product with H transpose turns out to be 0, everything fine. If it's not 0, something went wrong. Sorry, I didn't quite understand. So here's the question for the G matrix, if we can have a row 0, 0, 1. Well, we could have, but then our H matrix would be different. Yes, yes. So there's this direct relationship. Maybe also let me repeat the question for the Kazan students. So here was the question if we can have the row 0, 0, 1 in the G matrix. And the answer was, of course, we can have also this row in the G matrix, but then the H matrix would look different. As there's the direct relationship between G and H, so as we have the condition that the rows of H must be orthogonal to those of G. And this we actually did not derive, I just provided you this, some result from linear algebra, how we can get this matrix H where the rows are orthogonal of G. And we get this by using this parity matrix transpose with minus here actually if we consider more general codes even. So here was the question in advance, if I could explain again what's up with this minus. So for us, where we talk about the binary cases only, where just zeros and ones, this minus doesn't matter at all, because if I have the 0 minus 1 in the modulo 2 space, I get the plus 1 again. So in modulo 2, the minus doesn't matter. But for example, we could also think about like ternary codes where we have 3 possible states like 0, 1, and 2. There we would actually have to consider this minus here to make sure we get this orthogonality between. So there's also one simple example for ternary codes. For example, you might know the Morse alphabet. You have the short symbol, you have the long symbol, and you have breaks in between. So the Morse alphabet would be the most simple example for ternary code. But in most practical applications, we actually stick to the binary codes. This is also why we talk here only or mainly about binary codes in the lecture. And then you can forget about this minus. Okay, so if we do it this way, we made it with an example. So how to get from this matrix G to the matrix H. We need the transpose of this parity matrix, which goes in here at the beginning of H, followed by an identity matrix. And now you could actually verify it. Now each of these rows of G should be orthogonal to the rows of H. Maybe just verify it briefly. First row here, first row here. 1 times 1 is 1, 0, 0, 0. Product will be 0. 1 times 1 is 1. So we get 1 from the first one plus 1 from this one is 0 in the modulo 2 space, and 0 here and 0 here as the product. So here it's obvious first row from here is orthogonal to first row from here. And if you verify it, it will be orthogonal to all other rows. And today we will actually see how we deal with this parity check matrix. So if I receive any sequence y here, in our case y is one of the valid code words, and I multiply with H transpose, the result will be 0, 0 vector here in this case, which means y is a valid code word. Maybe going back to our drawing. So if I receive now a sequence here in our example, for example, of 1, 1, 1, 0, multiply with H transpose, it is orthogonal, result will be 0, so I can tell 1, 1, 0 is a valid code. For example, if I had a received sequence of 1, 1, 1, I would multiply it with H transpose, 1, 1, 1 times 0, 0, 1. The result will be 1, so it's different from 0. So I can tell 1, 1, 1 is not a valid code word. It's not in the space which is spanned by the rows of G. Okay, so this is basically where we stopped last time. And today we want to see how to deal with this result here, with the so-called syndrome, how to get the most likely error pattern if we look at this vector S. Okay, so yes, are there questions? Yes. Okay, also let me repeat this for the Kazan students. So here was the question, what's the advantage of increasing the number of parity bits, of check bits? Yes, and the answer is, if we increase the number of check bits, we will get a code with a larger minimum Hamming distance. Just imagine again our example with the repetition code. If I have like the 3 times repetition code, I have 1 bit, 2 additional parity bits, I get a minimum Hamming distance of 3. I can correct single errors. If I consider the 5 times repetition code, I would add 4 additional bits. I spend more parity bits. I would get a minimum Hamming distance of 5 between my 2 possible code words. I could correct double errors. So by increasing the number of parity bits, I typically get a larger minimum Hamming distance, my code will be more powerful in terms of the number of errors it can correct. Yes. So up to now, we basically only considered examples where we can correct single errors. The 7,4 Hamming code had a minimum Hamming distance of 3, so it can correct single errors. And also our 3 times repetition code had a minimum Hamming distance of 3, which can correct single errors. Of course, more powerful codes will have a larger minimum Hamming distance, but so far we did not get to know more powerful. But we could get more powerful codes by using more parity bits. Sure if I understand it correctly, but actually today in one of the tasks we will get to know a code with a minimum Hamming distance of 4, but still we know also with 4 we can only get single errors. But we could think about an example where we have larger Hamming distances and double errors, but then of course the examples will be also bigger. It's difficult to write down the set of code words if you is basically the space of your code. Okay. So let's see. So before we continue with the theory, we come to some tasks to solve today. Is this one here first? So I had a look at the task collection, which would be good to solve today. So there are some very easy tasks where you basically just have to put numbers in the equations that we have. So this we will not solve here. So we want to solve, let's see, one with the cross parity check code. Of course, this is also related to the homework assignment. So here we consider a 2516 cross parity check code. So this means the code words are of length 25, and we have 16 information bits and 9 parity bits. So this is an example for a larger code, and we will see how this one performs. Cross parity check code. So task A, we should determine the code rate. And the redundancy. It's RC, so the redundancy of the code. And the relative redundancy. Case RC. Okay, well, code rate R, this is straightforward. It's K divided by N. So 16 by 20. Actually, I did not solve this further. So the redundancy is basically the number of bits that we append. So we transmit 16, or we want to transmit 16 information bits, and we use a code word of length 25. So this means we have 9 redundant bits. And the relative redundancy, this is RC, sure, so it by say 9 divided. Okay, so just some properties of this code describing how much redundancy we add in order to hopefully correct as many errors as possible. Then we should come up with the parity bits for an arbitrary example. Parity bits. Example. And the structure of this cross parity check codes is straightforward. Basically a range for bits in an angular shape, and we for the rows and for the columns, and with this we can tell positions of errors, as we will see. Just coming up with an example. So we need 16 information bits arranged in matrix. Just take some random ones. Could be any combination. Those are my information bits that I want to transmit. Info bits. Actually the K information bits, so 16. Info bits. Information that we would like to transmit. And now we simply calculate the modulo 2 sums of the rows and the columns. So for the first row, we have 0 plus 1 plus 0 plus 1, 0. Second row, 0 plus 0 plus 1 plus 0. 0 here. 0 here. And we do the same for the columns. We get a 1 here. 1 here. 0 here. And now you could wonder about the last one here down in the corner. So yeah, you can interpret this either as additional parity bit for this column of parity bits or for this row of parity bits, or you could also see easily it's just the modulo 2 sum of all addition bits. In any case, it will turn out to be 1. These are my check bits, my parity bits. M being check bits or parity bits. Now, of course, for transmission, we would like arrange them in a different way. So the code word would look like this, followed by transmitted code word. this was basically already task B. We just should calculate this parity bits. And now task C becomes more interesting. Now we should introduce errors that occur during transmission and see if we can identify the errors. Yes. Okay. So here's basically just the question, how to arrange these bits now in the code word. Well, as long as you know how to do it or how you did it, the decoder knows where to find the bits, it's fine. So it doesn't matter if we fill basically this green bits here, like row-wise or column-wise. We just need to do it somehow. Also for the parity bits, we just need to make sure that the receiver knows where to find the parity bits. So of course, we would somehow define this, for example, P0, P1, P2, and then of course here P0, P1. So just need to make sure that we know. Okay, so we transmit this guy now. Let's see. Transmit. And now let me introduce a wrong bit, right? Basically the same ones again. Introducing this one. Just imagine we receive here a 0 bit instead of the 1 bit that we actually transmitted. Remaining ones should be the same, so no errors there. We would also, we assume we receive our check bits correctly. So just a single error occurred now. Example. This will be the received and rearranged. What we do is straightforward. We recalculate our parity bits and see where we get a mismatch. Basically need this means for the first one I get 0 plus 1 plus 0 plus 1 is 0. For this one I get 0 plus 0 plus 0 plus 0. 0, 0. And next we just need to compare our recalculated parity bits with the received parity bits to see where we got a mismatch. mismatch. Error must have occurred. So we know something went wrong, second row, something went wrong, second column, in the third column. Actually, from this, we can tell that this bit must be wrong. This simple error correcting scheme, we identify correct single errors. Yes, and actually task D is one for you. You can think about this. Now we should think about what happens if we introduce more than, for example, imagine the one next to this guy could be also wrong. Then we will get a mismatch in this column. But if we have two wrong bits here, actually here, we will not get a mismatch in the parity, because the one here would basically make the parity bit again the same as we had it before. So already, if we have two errors now in one row or in one column, our coding scheme would fail. At least not in any case it could correct double errors. So maybe we find cases where it can, but actually not. So if you imagine, let's say this one here and the one down here, we'll get a mismatch in this column, this row, and in this row, which means any of these 4 bits could be wrong. 2 out of these 4 bits can be wrong. So already if we have more than 1 bit wrong, we will get difficulties with this coding scheme. A stronger coding scheme, we just get decoding it. This is quite an interesting coding scheme, also quite easy to understand. And this is also like the one that is used in your homework assignment, this MATLAB assignment, just a smaller one that it is easy for you. So write down possible code words. The decoding is also done more easily in your homework assignment, so you don't need to think about the calculation of the parity bits, as we just do a maximum likelihood decoding by calculating distances to all possible received coordinates. Of course, you could also think about decoding routine like this, but you don't have. Okay. Are there questions related to this one? You can also generate examples where one of the parity bits is transmitted wrong. Maybe this is also interesting if we assume this one was transmitted correctly and maybe the parity bit is wrong. So what will happen then? We will get all column check bits correctly because here no error occurred. But we will get a mismatch here with this parity bit and the calculated parity bit. So all columns correct, but a mismatch here can only be a wrong parity bit. So we can also identify errors in the parity bits. Okay, but this just as remark. So then we have a solve before. It's 3.9. So task 9. So there we want to think a little bit more about the generator matrices. So determine G, H, so the generator matrix and the parity check matrix. Disk A, n,1 repetition code. And task B, n, n-1 single parity check code. So, and here we have another question from Kazan. So why we use 16 information symbols in the previous code? Well, 16 just because we can arrange them nicely in a rectangular shape. It's like 4 by. We also have like a 15 information symbols. So then we would get like 3 rows and 5 columns. Of course, then it will also work. Any number of symbols that we can arrange in a rectangular shape, it makes sense to apply this kind of cross-parity check code. Here the question why actually this is also a good question. So of course we could also think about if we need this 9th one. Probably it will also work nicely with 8 control bits only. But that's also a good one for you to think about it. If we really require this one down in the corner, maybe to find errors in the parity, or if we don't need this one. Actually, a little bit about it, we will see that this one will actually have an influence on the Hamming distance, on the minimum Hamming distance. Just imagine the all 0 code word, so having zeros here for our information bits. Then also all the parity bits will be 0, so this will be the all 0 code. And the one being most similar, the all 0 code, we will get it if we introduce a single 1 here. Introducing a single 1 will give me a 1 here in parity, a 1 here in the column parity, and a 1 here in this overall parity. So this means the code word being most similar to the all 0 code word will contain 4 ones in this case. So this code will have a minimum Hamming distance of 4. So 4 is also just enough to correct single errors, because in 2 errors we could have cases where we don't know how to decide. Just imagine the 4 times repetition code. If you have 0, 0, 1, 1, you don't know what this one. If we would skip this last one here, we would get just the minimum Hamming distance of 3. We still would be able to correct single errors, but the benefit of having the minimum Hamming distance of 4 is that we would be able to detect 3 wrong bits in the code. We would not correct them, but we would detect 3 errors in the code bit, whereas in the case where we don't transmit this one and we had distance of 3 errors in the code word would result already in another valid code word. So we would have no chance to detect 3 errors. So by introducing this 4th or this 9th check bit here, we get the minimum Hamming distance of 4 instead of 3, which will make it possible to detect 3 wrong bits. So it's a bit more powerful if we actually introduce here this 9th parity check bit. Question. Okay. So let's come back to this one. We are interested in the generator matrix of this repetition code. Maybe it's easy to start again with an example. So I want to encode, for example, U being just a single one, and I expect then the code word A to be the one I transmitted plus 2 times repeated the same one. So let's see how we can write this as matrix vector product. Is A being U times G. Question is just very simple. What do I have to multiply with 1 such that the result be a 1, 1, 1? So actually, in this case, our matrix G will just be a vector. Yeah, so notice a 1 here, 1 times 1, this will end up here. And of course, we just need the same bit, just once make sure that the bit directly mapped in the. At a 0 here, I will get a 1 times 0, 0, 1 times 0. It will turn out to 0, 0, 0 code. So this is very easy. This is then parity matrix P, and we get H by the transpose followed by an identity matrix. So meaning H so P transpose will be the column vector 1, 1 followed by an identity matrix. And this way we get actually now, as we explained before, the rows of H being orthogonal to the rows of G. Let's see if this works. 1 times 1 plus 1 times 1 plus 0 times 1. This is 0, and also for the, again, rows of G being orthogonal to the rows of H. And now we could use H again to verify received sequences if they are valid code words. So for example, if I multiply the valid code word 1, 1, 1 with H transpose, the result will be 0. But we will get some more practice. Okay. Next one is maybe a bit more difficult. General example, we have n code words of length n. We have n minus 1 info bits. Also simple example to get the idea how to get to the general one. Start with U. Assume we have 4 information bits that we would like to encode with this single parity check code. And we already know this. The parity bit will be the modulo 2 sum of information bits. 1 plus 1 plus 1. And now maybe it's a good exercise for you. Try to solve this on your own. I'm asking again for the generator matrix. that will give me the corresponding result, so U times G. Generator matrix G, and the result should be A. So how does this matrix G needs to look like? Try to solve this on your own. 2 minutes to solve this. You should see this right away. So in the example that I've drawn here, 5 check code word length 5 nation bits, 1 parity, single parity. Minimum Hamming distance for this one. Oh. And also think about the parity check matrix H. should be finished. It's not really so difficult. If I use the example that we had before, encode these 4 guys here. If I want to appear, these 4 bits to appear directly as a part of the code word, so I get this with an identity matrix here. This will map the bits directly in the code word. And if I want the last one to be the sum of all our information bits, I need like 1 times the first bit, plus 1 times the second bit, plus 1 times the third one, plus 1 times the fourth one. And you see in our case, this will turn out 1. Generator matrix, I could also provide it in a general form now. It's the identity matrix of size k, so number of information bits, followed by this column. This will be true for all single parity check codes, where now this vector with 1s is our parity matrix P, the parity matrix transpose. This is P transpose, followed by an identity matrix. This will be an additional one. Parity check matrix will in this case be just this vector. Yes, we always talk about modulo signs. Okay, are there questions related to this? Just 2 simple examples to give you a better feeling about this generator matrix, and you will get to know this parity check matrix. Next part of the lecture, where we talk about the decoding, where we use this parity check matrix. Okay, let us continue with the decoding. Yes. So here was the question about the minimum Hamming distance, and we could simply again see this by looking at the generator matrix G. So we basically know all rows of G are valid code words, and the all 0 code word is a valid code word. So if we look at the one being most similar to the all 0 code word, we will get it by introducing a single 1 here, which will also give the parity 1. So this means we get a minimum Hamming distance of 2. So this means our code is not powerful enough to correct single errors, it just can detect single errors. For example, if we see a mismatch in the parity bit, we cannot tell which of the bits caused this error. This means we cannot, but we see something went. So those types of error correction schemes are typically used for schemes which have like an automatic repeat request. So we see the parity does not match, so we ask for a retransmission of the packet. This would be the most simple method to correct errors. So here's the question, if we can have different parity matrices. Well, of course, the parity matrix depends on the error correction scheme. So you could try thinking about what if we add some additional security here by adding 1 more column to this parity matrix. So just the most easy case will be just adding another column here containing 1s. This would basically just repeat the bit once more, which would actually give us minimum Hamming distance of 3 already. Then it would be possible to correct single errors. So how this parity matrix looks like, this really depends on the coding scheme. We already know matrix for the Hamming code. So based on Hamming's smart idea how to calculate the parity bits in a good way, we know how this looks like for our single parity check code. We know it for the repetition code. So different codes, different parity matrices, different error correction capabilities. Let's start talking about the decoding. That's the more interesting part. Decoding using so-called standard arrays. So far, we only treated very small coding schemes, like with a fairly small set of code words. But if we have like sets of 1 million code words, of course, we need to think about some smart method how to decode it. Also in your homework assignment, you will calculate Euclidean distances as comparing 16 different code words. This is fairly easy, but I would not like to calculate 1 million Euclidean distances to decode one of the code words. So there we need to come up with something more smart. This we will get to know. Starting with the so-called syndrome calculation. So S H transpose. So S being the syndrome. So here, if Y is a valid code word, which means i.e. error occurs. The syndrome will be 0. Zero vector. This is just a consequence how we generated this parity check matrix H. And Y is basically the received sequence. This way. So right now we are just thinking in decided bits, additive white Gaussian noise model, or just thinking about zeros and ones. So we get this from certain transmitted code word A plus some error pattern E. Example, if we transmit, again, thinking about the repetition code, 1, 1, 1. And we want to model the case, for example, where the last bit gets corrupted, gets received wrongly. This would mean we have an error pattern of this. And if we add those two guys, at Y being 1 plus 0, 1 plus 1, 0. 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 1 plus This is basically now how we model our errors by adding this kind of error pattern. See, everywhere where I have a 1 in this error pattern, the bit will be flipped. It's wrong in this case. This means we also know that our received word A can be modeled as the transmitted sequence plus this error pattern. Putting this in our first equation, the syndrome is then A is E times H transpose. Multiply this out. Always be a bit careful if you multiplications in this vector matrix equations, but here it's gonna work like this. It's A times H transpose. It's E is H transpose. And here we basically see again, we have a valid code word A multiplied with H transpose, it will be 0. The code words are orthogonal of H or the columns of H transpose. This will be 0. So this means our syndrome just E is H transpose. Here we basically see that the syndrome just depend on syndrome just depends the error pattern. This means for our example, if I transmit a 1, 1, 1, and the last bit is wrong, I will get the same syndrome as if I transmit 0, 0, 0, and the last bit is wrong. See, we get the same syndrome for different errors that we model. We will also get to this in an example where we can write all possible code words and see how to explain this. So if we have different code words with the error being at the same position, so meaning the same error pattern, we will get the same syndrome. This will become more clear in an example. Also here you see that the 0 error pattern, where's the mouse pointer here? The error pattern is 0, 0, 0. Our received sequence will be a valid code word. Error pattern 0, 0, 0. This product will be 0, syndrome 0, meaning no error. So for the no error case, of course, this will work. So now let's look a bit more about the dimensions. So we have k information bits. So this means we get 2 to the power of k valid code words. We have a code word length. This means we get 2 to the power of n possible received sequences. and we have M being n minus k check bits. So we can get 2 to the power of n minus k possible syndromes. Brought the numbers here for the 7,4 Hamming code. Two to the power of 4, 16 possible code words. Code words of length 7. Errors could occur everywhere. This means 128 possible received sequences. It's 128 possible received sequences. We have 16 valid code words, which means 112 wrong sequences that we could observe at the receiver. 12 wrong sequences. And we have 3 parity bits. This means we have 8 different syndromes. This means obviously we have quite many sequences, wrong sequences, that must have the same syndrome. So there cannot be a unique mapping between 8 syndromes and 112 or overall 128 possible received sequences. See this in example. It's the example, then it. So we define the so-called cosets. It's this calligraphic M here, M mu, the coset mu. Those are the error patterns for which we get the same syndrome. E times H transpose is equal to S mu. Error patterns. Yield. Syndrome S mu. Example, 1 out of these 8 syndromes, and we will have any 16 error patterns that will have the same syndrome. This we come to an example which is again small enough such that we can write down all example. I use a 5,2 code. For code word length 5, we have 2 information bits. This means we have 4 possible valid code words. Generator matrix, so it should be a systematic code, so it will start with the identity matrix. And I just made one up. So this is a famous one or a especially good one, just one which is small enough. So I use one where basically just the first bit is repeated. Then we have the parity bit, so the modulo 2 sum of both information bits, and then the second bit repeated. So it's like a mixture between a repetition code and a single parity check code. And we know H. This will start with P transpose. Followed by an identity matrix. Let me start writing down the set of code words, gamma. So if I encode, I just do this now in my mind. If I encode a 0, 0, of course also the first one repeated will be 0, parity will be 0, and the second one repeated will be 0. If I encode a 0, 1, first one is the first bit repeated, the second one is the parity, and the third one is the last repeated. If I encode the 1, 0, repeating the first one, parity bit repeating the second one. And if I encode 1, 1, repeating the first one, parity bit repeating the second. So very simple coding scheme. And we have possible received sequences. Receive this one. This one. Receive all possible sequences Y. It's a mixture. See, here was the question if this is a parity check code. You look at this generator matrix, you see this 1, 0 here just maps the first information bit here as a parity. The 1, 1 here basically calculates the parity over my information bits, and the 0, 1 here maps the second information bit in the. It's just to make up arbitrary example. Calculate. Syndromes. Basically by E times H transpose. And of course, E can also be. So our error patterns, this would be the case no error occurs. This would be the case the last bit wrong, and so on. we basically arrange this in a table. So where I start here with mu column, which I will explain later. And here we will get this cosets M mu. Basically the error patterns which have same syndrome. Syndrome S mu. First one, what is going on? So if the syndrome is 0, we know we have a valid code word. So if I calculate the syndrome for any of the members of gamma, the syndrome will be 0. So this coset M mu will contain the valid code words. I calculate the syndrome for any of these patterns. The syndrome will be 0. And I basically do this for all other error patterns. Yeah, let's maybe just calculate it as example for one. Now I want to calculate E using the one where the last bit is wrong times H transpose. H transpose will be 1, 0, 0, 1, 0, 1, 0, 0, 0, 1. Result will be syndrome. So let's see what we get. So the first 4 don't play a role. Product will be 0. So just the last one. So this will give me the syndrome 0, 0, 1. So for mu being 1, so we already found one member of this coset M1, and it is the error pattern 0, 0, 0, 0, 1. So for any valid code word that I transmit, if the last bit is wrong, we will get this syndrome 0, 0. So then we basically would have to calculate S for all and so for example, we will also see that the error pattern 1, 0, 1, 1, 1. Also this, if I multiply it with H transpose, it will turn out to be 0, 0, 1. This will give me the same syndrome 0, 1, 0, 1, 0. This will give me the same syndrome 1, 1, 0, 0, 0. Will give the same syndrome. calculate this for. This is written so nicely. It's not an A, it's an E. It's nicely. We know this 4 error patterns will have the syndrome 001. And now the question is just which error pattern most likely occurs. We calculate the syndrome 001. See, in this case, just 1 error occurred. We also would get this syndrome if 4 errors occurred, but it's more unlikely that 4 errors occur. So from looking at this coset, just the same syndrome here, the most likely case that appeared is this one, namely just that the last bit is wrong. So we select this one as so-called coset leader. So the one with the lowest number of ones. Finally, we can sample. Yes. Minus the number of valid codes. Here was the question if the number of received sequences is equal to yes, so again the question, the relationship of the number of received sequences and the number of errors that can occur. Of course, within this number of possibly received sequences here, in this case like 108, there are also 16 valid code words. Of course, in this case, no errors occur, but in this 128 possible received sequences, there are 112 which must be wrong. Just here, our example is a bit smaller. Just 2 minutes left, but we can get this decoding example done. Example. Assume we receive now any sequence here. I use the 4 times 1, 0. Did an error occur? Which bit might be wrong? Which bit is most likely wrong? And in order to figure this out, I multiply received sequence S H transpose H transpose. I don't write this. So if we do this, we get the syndrome S being 0, 1. And with this, we look up coset leader. There I should show you the table. It's on the lecture slides. So with the syndrome being 0, 1, 1, it's this orange row here, the most likely error pattern is the 0, 1, 0, 0, 0. So most likely, if we observe this received sequence Y, the second bit was wrong. Let's see. Look up coset leader. So we get an error pattern being 0, 1, 0, 0, 0. This means most likely second bit. So, and we can correct our error simply by adding Y with the error pattern 0, 1, 0, 0, 0. And this will give me my estimated code word 1. So you see this just flips again. It's the very likely wrong bit. Make it correct this way. This is the most likely transmitted code word. This is basically how we use this coset table. It's a grouping of error patterns which will yield the same syndrome. How we can use this to correct the errors that most likely occur. So just going this set. So we would also get the same syndrome if the first 4 bits were wrong with this error pattern. So if we transmit a 1, 0, 1, 1, 0, and we receive a 0, 1, 0, 0, 0, we would get the same syndrome. But this is way more unlikely to happen as just this single error here at the second position. This is the whole idea of this factorization in the cosets to find most likely error patterns. Okay, so we will repeat this again briefly next time because this was quite fast now, but I think then we should be able to extend this. Okay, and also have a look at the lecture slides. There you find the whole coset, and also probably next time speak about this slide, how to get these cosets even more easily as compared to this brute force approach that I described here by calculating just the syndromes for all possible errors. So there's a more easy way how to get this coset table, but we will get to know this next time. So in any case, the brute force approach will work calculated just for each of them. Okay, are there questions related to this one? Yes. Yes, so here's a question related to the error pattern. So the error pattern basically describe or are used to model errors. So you see where we have a 1 in the error pattern, this will basically model the error where this, in this case, the last bit is transmitted wrong. So ones in the error pattern will flip the bits that we actually transmit and introduce errors this way. And the all zero error pattern basically means we have no error during transmission. So if you see, if we add all zeros here in our model, the received sequence will be the same as the transmitted one. Basically, looking at all error patterns, we will basically also get the all zero error pattern, which will have the consequence that, yes, in this case, the received sequence Y is exactly the same as what I transmitted. This is the case, no error occurs. This is the case, the last bit is flipped, and so on. So I have this case 2 to the power of 5, like 128, 64 possible error patterns. Was this the question, or didn't I understand it? Okay, some more questions. Okay, so then we are done for today. Remember, next week we have a online class. Here you find the link again. And yes, so then thank you for your attention. Again next week in our WebEx room. Okay, so then enjoy the rest of the day. Goodbye and see you next week.